You want metric threads? You want metric threads. Okay, we'll do metric threads. Welcome back to Cloud 42, I'm James. I am in the middle of developing an electronic lead screw for my lathe, which is a device that replaces the change gears with an electronic controller and a motor. In the last video, we finally got the whole thing running end to end, and we cut some imperial threads in steel. But if you live outside of the US or Liberia or Myanmar, you probably left a comment on that video asking me if this system would also do metric threads. The answer is yes, and that's what we're going to look at today. But before we do that, I have some unfinished business with some pulleys. You'll recall that I purchased these aluminum timing pulleys for the drivetrain to hook the stepper motor or the servo up to the lead screw on the lathe, and I purchased them with the wrong size bore. Somehow I got in my head they were 16 millimeter, but the shafts are actually 14 millimeter. So I ordered some replacements, and they are now here. Now these pulleys come with a smooth bore, but the shaft on the lathe has a 5 millimeter key in it. So I cut keyways in these pulleys. I couldn't find pulleys I could purchase that already had the keyways in them, so I had to cut them myself. And I did another video on this topic, so I'll link that in here. You can go watch that if you want. But the idea is I've got a tool with a single cutting tooth on it, and I did this in the CNC mill, just plunging this repeatedly through the slot to cut out the keyway, just pulling off one chip at a time, a couple thou at a time, working back and forth and working gradually in and cutting that keyway, scraping it out. It's called vertical shaping. Sometimes it's called single point broaching. Anyway, there's another video you can go look at if you are interested in that. Now these two pulleys are fine. These are for this is the 48 tooth and the 72 tooth, this one for the stepper, this one for the servo, that just go on the input shaft, because they just go on with the keyway and are captured with a screw in the end. I don't know if you can see, but I did line up one of the set screw holes in the pulley so that it would bear down on the key if I ever decide to do that. I don't think in this application I need that, but I went ahead and lined it up that way because that's typically how you would want to do that. Let the set screw bear on the key and not on the shaft. Now the last pulley here is the GT2 pulley for the to drive the encoder off of the first idler gear, and this one I had to modify. This is how it came from the factory. You can see it's a normal 6 millimeter pulley, so there's like 7 millimeters of material plus a couple millimeter or millimeter and a half flanges, plus a boss with set screws in it. And of course, I can't find a pulley that I really need, the one I need, which would be only 8 millimeters thick. So I just grabbed this in the lathe and grabbed it very gently by this outer ring. The flanges are just pressed on, so you have to be very careful. Grabbed it by the outer ring, turned all the material and the ring off of this side. I actually broke the ring off first with pliers, turned it down, and then turned it around and thinned down the flange on the other side. And this is what I ended up with. So I've got a very thin, like 1 millimeter or a little bit less than a millimeter flange, and about 7 millimeters of pulley tooth left. And then this has the same keyway cut in it, and this will go on that first idler shaft for the encoder. So let's go put these on the lathe. Okay, let's start with the 3D printed pulley here on the input shaft. Just take some tension off of the belt here. Take out the locking screw. Now the 3D printed pulley actually did fairly well. I'm not really seeing any major problems with it. You can see just a little bit of evidence of pressure from the key in the plastic, but all in all, it's not too bad. This might actually have worked long term. I'm not really sure. I prefer the aluminum because I know it's going to wear better. So I got the aluminum pulley, line up the key, and that fits beautifully. I act like I'm surprised. I am a little bit. Snug that down so it won't go anywhere. And tension up the belt. These don't have to be super tight. Yeah, that's plenty. It's not going to slip off. Okay. Next up, the timing pulley here. Now I am going to actually take the encoder off the lathe. Oh, look at that. Maybe I should power this off. Okay, I'll set that up out of the way, and the first trick is going to be to get this little E-clip off. I don't know who invented E-clips, but yeah, the plastic's already starting to get scored there a little bit from where the E was rubbing on the E-clip. I'll go grab the metal one. And that is running nice and straight, a lot straighter than the plastic one. The plastic one, for whatever reason, was wobbling a little bit. I don't know if it warped or if it's just a matter of little dingleberries and other kind of artifacts on the surface. But in any case, both of these are running way truer than the plastic ones did. Let's put this back on with the belt. Okay, that looks good. And again, because it runs truer, I can run the belt a little tighter. I don't have to have slack in it. Okay, let's turn this back on. Make sure everything looks good. And the belt looks like it's tracking beautifully. Both belts are tracking. Looks good. Now I think we're ready to cut some threads. My lathe has an imperial lead screw. Specifically, this lead screw is 12 threads per inch. And so when the lathe is turning and when I'm threading, this screw pulls the carriage along to cut the thread. So right now it's free, but if I close the half nut, then the half nut, which is down here in the apron, locks onto that screw, and as the screw turns, it pulls the carriage along. So if I'm cutting a thread on a piece of material, and I wish I had something with bigger threads on it so you could see it better, but this is a piece of threaded rod, and if I want to, as the spindle is turning, follow that thread along and cut it in the material, I need to have the lead screw turning at the right rate in relation to the spindle so that I carry along with the thread I'm trying to cut. Now, if I'm trying to cut 12 threads per inch, it's easy because this screw's already 12 threads per inch. So if it spins at the same speed as the spindle, then this will come along 12 threads per inch and this will cut 12 threads per inch. But if I want to cut a different thread, like what if I wanted to cut 6 threads per inch? Well, I need the lead screw to turn twice as fast, so I'll move twice as fast along here and cut half as many threads. Or if I wanted 24 threads per inch, I would need this to run half the speed of the spindle so that it moves more slowly and I cut a finer thread. And so that's basically what the change gears do, and that's what the electronic controller and the electronic lead screw does, is it just varies the ratio between the speed of the spindle and the speed of the lead screw so that we pull the apron across and pull the carriage and the cutter across at the right speed to cut the right thread. And that's fine for a single pass. But when we get to the end of the pass and we want to disengage and move back for another pass, we have to, well, we don't have to, but we usually want to unlock the half nut and then roll the carriage so that we don't have to stop and reverse the spindle. Now, in order to do that, we need to re-engage this carriage at the right point. Now, if I were cutting 12 threads per inch, it would be no big deal because I could re-engage on any groove of the lead screw and I would be in a thread that I already cut. So if I make a pass, 12 threads per inch, those are lined up with the 12 threads per inch here. I can just unlock, move over, drop it in, and I'm good to go. But if I'm not cutting 12 threads per inch, then it gets a lot more complicated. So if I'm cutting 24 threads per inch, we're still good, right? Because there's 12 threads per inch here, but if I come over and land on this multiple of 12, that's also going to be a multiple of 24, and that's fine. Any place that we land on this lead screw is going to be in a thread. But if I'm going the other way and I'm cutting 6 threads per inch, I can't drop into just any thread here. I can only drop into every other one, and I need to know exactly which one it is. Because if I'm cutting 6 threads per inch and I drop into the wrong thread here, I'll be right in the middle and I'll destroy the thread. So this is where the threading dial comes in. And the idea with the threading dial is that while this is locked and while it's moving, this doesn't change. Whatever number it's locked on, it's going to stay locked on, because this shaft has a gear that you can see back down here in the bottom that engages with the lead screw. As long as the half nut's closed, the carriage is moving at the same speed of the screw, so this doesn't turn. But as soon as I unlock the half nut and start moving the carriage, you can see that the threading dial is turning. And that's because this 48 tooth gear on the bottom here is engaged with the lead screw. So whenever I move relative to the lead screw, it turns just to show me how far I've moved on the lead screw. And the purpose of this is so that depending on what thread I'm cutting, I can move along and find the correct point to re-engage. So let's talk about what's going on here. This particular dial has 12 divisions, 1 through 12, but they're marked 1, 3, 5, 7, 9, and 11, and then the ones in between are unmarked. So if you look at the threading dial on the lathe, it's on the front here, I'll put up a graphic, it says that for certain threads, I can engage any point on the scale, 1 through 12. But for other threads, I can only engage 1, 4, 7, and 10. So this is 1, that's 4, 7, and 10. So why is that? What's going on with that 1, 4, 7, and 10? Why is that special? Well, let's think about this for a minute. This on the bottom here is a 48 tooth gear. And I've got 12 divisions up here on the dial. So what that means is that every mark on this dial is 4 teeth or 4 threads on the lead screw. So if I move this one position, I've moved it 4 threads. So if I move it 3 positions, like from 1 to 4 or 4 to 7 or 7 to 9 or 9 to 1, then I've moved it 3 times that, I've moved it 12 threads. And that's not an accident. It's a 12 thread per inch lead screw, and if I move between any of these marks that they've listed, 1, 4, 7, and 10, I'm going to move 12 threads, which is exactly 1 inch. And let's just validate that that's true with the dial indicator. So throw the dial indicator on here. Let me engage it on 1, take out the backlash, and set that so that is on 0. You know what, let me move that to where it's easier for you to see. I'll put it right at the bottom so that that lines up better with your line of sight. There we go. So you can see that it's on 0. Now I'm on 1 here. Let me go ahead and move it to 4. So there's 100, 200, 300, 400, 500, 600, 700, 800, 900, and here we are coming up on 4. We'll engage, and we're 1 thou shy. There's a little bit of error in the screw, or there's some slack in the system. And so we've gone from 1 to 4, and we've gone exactly 1 inch. And that makes sense because we've gone a quarter of a turn, it's 48 tooth gear, so we've moved 12 teeth, and it's 12 threads per inch. So that's what's going on with this 1, 4, 7, and 10. If you just engage on 1, 4, 7, and 10, you'll always be hitting this lead screw on a multiple of 1 inch. And if you're cutting imperial threads, that will work for any whole number thread. Think about it for a minute. If I'm cutting 13 threads per inch, then 1 inch will be exactly 13 threads. If I'm cutting 3 threads per inch, 1 inch will be exactly 3 threads. So as long as I move 1 inch, I will always land exactly in one of my threads if I'm cutting a whole number thread. Now, if we look back at the chart, there are certain threads that I can engage on any number. Well, why is that? Well, the reason for that is because most of these are multiples of 3. So I know one number is not going to be an inch, it's going to be a third of an inch. If going 3 numbers gives me an inch, then going 1 number on the dial gives me a third of an inch. Well, these are all multiples of 3, 9, 12, 18, 24, 36. So if I just go a third of an inch, I know on these particular threads, I'm going to land in one of the threads. Now, you'll also note the half threads, 9.5, 11.5, 13.5. Well, those you can't engage on any one of these quarters, 1, 4, 7, and 10. They have listed here just 1 and 7, or you could also do just 4 and 10. But the idea being, instead of going a quarter dial, you have to go the full half dial, and that's because of the half thread. If it were 9 threads per inch, then moving 1 inch would land me exactly in another thread. But since it's 9.5, I can't go 1 inch. I've actually got to go 2 inches before I'll line up. If I go just 1 inch, I'll end up on the half thread. Anyway, that's what happens for imperial threads. Now, if you had a metric lead screw and you were cutting metric threads, you would have a very similar situation, where there would be some nice, neat math, there'd be some particular numbers you could land on, and you'd always land in the thread and be good. But in this case, what I'm going to be doing is cutting hybrid threads, where I have an imperial lead screw, but I'm going to cut a metric thread. Now, the same issue arises if you have a metric lead screw and you need to cut imperial threads. The math is not nearly as nice. It does not add up as well. So if I want to unlock, if I'm cutting a metric thread and I want to unlock the lead screw and I want to move it over and lock it into another groove on the lead screw, then I have to move over an amount where my 1/12 of an inch thread lines up as an exact multiple of the pitch of the screw I'm trying to cut, which in this case would be metric. So if I'm trying to cut a 1 millimeter thread, but I have 12 threads per inch, how many 1/12ths of an inch do I have to move before I land up exactly on a 1 millimeter boundary? Well, the answer is a lot, because it's 25.4 millimeters per inch. Well, we don't have 0.4 of anything on any kind of screw or gear, so it would be 254 millimeters for 10 inches. 254 is 127 times 2, 127 is prime, so pretty much no matter what you do, if you want to be able to unlock the half nut, move over and relock on your imperial thread to cut a metric thread, you're going to have a gear down here on the threading dial with at least 127 teeth, or maybe 254 teeth, depending how the math works out. And that's just not practical, which is why you don't see it on the lathe. And so, as a practical matter, we're not going to be able to unlock the half nut, move over, and find the right thread to relock and be in time with our metric thread that we're trying to cut. And so this is why, when you're cutting hybrid threads, metric threads on an imperial lead screw or imperial threads with a metric lead screw, you typically just leave the half nut closed and reverse the lathe. And that's exactly what we're going to do today. This is the same workpiece that we had in the lathe last time, and these are the half 13 threads, but today we're going to do metric. So let's turn this down to 10 millimeters, and let's do a 10 by 1.5 millimeter thread. Nine 0.97, that will be perfect. Okay, as usual, let's start by putting in a gutter, so we have some place to run off into. Let's find our 0. Okay, we're all set up in 0. Let's cut some metric threads. So let's switch to metric and thread. So there's 0.5. Let's go 1.5 millimeter, which is what we're looking for. Make sure that lines up with the nut I have. Yes, it does. So we're set thread 1.5 millimeter, and we will engage the half nut, and we're going to leave the half nut engaged until we're done with this thread. So we'll start out nice and slow, and let's take 2 thou just for a scratch pass to make sure we're going in the right direction here and have the right pitch. Now stop the lathe and reverse it back out. Gonna go a little faster. And let's make sure that thread is correct. Yep, I can feel it. Okay, let's take 5 thou. Let's dial this back in first. Okay, 5 thou. Retract, reverse. Another 5 thou. Another 5. I wonder how close we're getting. Let's back this up enough to try a nut. Close. Let's try 2 thou more. And there we are. Metric threads with an imperial lead screw, and without having to mess around with change gears. Okay, let's do something crazy. Let's try left-hand metric threads. This one will test my hand-eye coordination and being able to turn this around. As usual, we'll turn it down first. Okay, let's cut a left-hand metric thread in this. So we'll switch over to threading. We'll switch to metric, and let's just do the same 1.5 millimeter. But we're going to hit the reverse switch. Oh, wrong button. Hit the reverse switch, and so now we'll feed the opposite direction away from the headstock. And let's start with, I gotta engage the half nuts here. Actually, let me, before I get too crazy, engage the half nut out here and make sure it's feeding the right direction. Yes, it is, and way too fast. Okay. Let's bring it in here. Engage the half nut. Again, it doesn't matter where we engage it. Bring this into 0, and let's make a pass. Retract and reverse the lathe. And I can always push the last little bit by hand there. Okay, let's take 5 thou. Oh, and I know I should have reversed the compound, but I'm not going to worry about that today. I'm going to thread this light. It's going to work anyway. Another 10. Now in reality, I don't actually have a left-hand nut. All I have is a right-hand nut, so I don't have any way to test this, but that appears to be working. It's not quite as clean as the other one, and I suspect that the reason for that is just because I didn't reverse the compound, so I was cutting on the trailing edge. But I am going to call that a success, and that is definitely a left-hand thread. Right hand, left hand. Nice. So for those of you who are asking, will this electronic lead screw setup do metric? Yes, it will, though you do have to consider whether you can unlock the half nuts or not, depending on what your lead screw is, whether you have a metric or imperial lead screw. And the software in the controller is configurable, so you can run it with a metric lead screw or with an imperial lead screw. The formulas are in there for both, so you can run that either way. But of course, when you're cutting hybrid threads, you have to leave the half nut locked. Well, that is all I have for you today. There is, of course, lots more coming. I have some prototype PC boards in the works, got those sent off to the fab, and I just got the first boards back. So next time we will assemble one of those and try it out. Hopefully we can ditch the breadboard and get the electronics on this thing one step closer to having a kit, so you can build one of these for your lathe. Well, if you're enjoying these videos, please give me a thumbs up. Feel free to subscribe to the channel and leave me a comment. I'd like to know what you think. Thank you for watching.